Hey everyone, I hope your test went well. I hope week 2 was okay. So I am here to give you kind of an introduction into what we're going to be looking at for week 3. So week 3 is primarily about applying what we know about derivatives and how to take them to their actual useful properties, because nothing in mathematics exists because we can do it, right? There's always a reason that we choose to do it. And so for derivatives, a lot of that is going to pop up in this week and a little bit of next week too, actually. So what we are going to look at is, I think it's 6 sections in total. All of them are going to be either more advanced ways of taking derivatives, so basically just more complex functions and different ways we can make that easier on ourselves. And then in addition, we'll also have some applications like rates of change, min-max values, things of that nature. So I'm just going to go through the sections and kind of give you an idea of what to expect in those and what to look for, kind of how to approach them and study them. I think that'll be the best way for these, because they're somewhat different since each one's a kind of a different application. So I want you to have a kind of a guideline system for what you're looking for when you start reading this material. So the first one that's up is implicit differentiation, and this is essentially how to differentiate functions where x and y are kind of mismatched together. So normally the way we have our equation set up is we have a y, right, and then we have a bunch of x stuff, right, and then we take the derivative of that, and if you want to think about it, right, if you take the derivative of y, right, you just get y prime, right, or dy dx, whichever one you prefer, right. So this side, right, is just a notational thing. This side's where all the fun happens, right. We have our chain rule, product rule, exponentials, all that kind of stuff, right, and that's what we use on that side. When they're mixed together, there's still a way we can take the derivative without solving for y. It's called implicit differentiation. And essentially what you're going to do is you're going to take the derivative of all the x's like normal. You're going to take derivatives of y just like you would take a derivative of x, except when you're done taking a derivative of y, you put a y prime after it. So for example, if I have x squared y, then what I would do is I would have to use the product rule there. So I would take the derivative of x squared, 2x, and then the y would be left alone. So derivative of the first times the second. So 2xy would be my first term in that product rule, plus, and then the x squared would be left there, and I'd have to take a derivative of y. Well, if I take a derivative of y, kind of imagine taking a derivative of x. Right? So if I take a derivative of just x, it's 1. So if I take the derivative of just y, it's 1. So I'll have x squared 1, but I took a derivative of y, so I have to put a y prime after it. So I'll have x squared times 1 times y prime, or just x squared y prime. And this is what we're going to do. And the way implicit differentiation works is we go through and we take the derivative of the whole thing like this, both the left and the right side of the equation, and then we try and solve for the y prime at the end. And so that's pretty much how that is going to work. The next thing you're going to come across is derivatives of logs. So you'll find the formula for how to take the derivative of a logarithmic function. Specifically, a natural log is the one you'll encounter the most. So ln, or log base e, and those formulas will be all in there. The other part of this is something called logarithmic differentiation, which is basically a way we can deal with either very complex functions that we want to take derivatives of, or functions where we have a function raised to a function, so like x raised to the x power, right? If we have something like e to the x, we know how to take that derivative, right? We have a number e and then x, and so we're good there. But if we have something like x raised to the x, right? We can't use the power rule because we can't do x minus 1. We have an exponent that's a variable, and so I think I need to switch these around. There we go. So we have an exponent that's a variable, and we have a base that's a variable, and so in that case we need some way to deal with that. Essentially what we're going to be doing is take the natural log of both sides. That allows us to bring our exponent down front with our log rules. We take a derivative with implicit differentiation, so the thing we learned before, and then we solve for y prime, and we're good to go, and that's our derivative. It also makes it much easier if we have a bunch of like roots and multiplication and fractions and all that stuff, because we can use our log rules, if you remember those, to split that up. Remember, if we have log of a plus log of b, and those logs have the same base, then we can smash those together into log of a times b. Well, it works in reverse too. So if I have log of a times b, then I can split that up into log of a plus log of b. And so if we know how to take derivatives of log functions, we can actually split that up by taking the natural log of both sides, applying our log rules, and it becomes much easier to differentiate. So that is what you'll discover in that. 3.7 and 3.8 we're going to skip for now. Exponential growth and decay is stuff you'll come across later. Rates of change in the natural and social sciences are essentially just what we've been learning with word problems, and as much fun as that is, and I mean that completely seriously with zero sarcasm, as much fun as that is, in a summer course some things have to get cut, and so that is one of the things that went on the chopping block. So the next thing we'll be doing is related rates, which is unironically and very truthfully my favorite thing in all of calculus. So remember that. The person who makes your tests just said that his favorite thing in all of calculus is related rates 3.9. Remember that. Okay, so what related rates are essentially algebra word problems, but with calculus sprinkled in. And so what you'll end up with is something like you have a balloon, right? You have a balloon, you're blowing it up with air, you have a, one of those hoses that connects to an air compressor, and so you get a constant rate of airflow in, and you can measure something like the circumference of the balloon. Just imagine it's spherical, right? So you can measure something like the circumference around, but you have no way of knowing how the radius is changing. And that's the big keyword with related rates. Something will always be changing. When we have algebra word problems, or the way we used to do it, Johnny has 14 bottles of soap, he gives 3 away. Why does he need 11 bottles of soap? That kind of thing. When we do that, nothing is changing, everything is kind of static. Here, if we're filling a balloon up with air, the balloon is constantly increasing. And so when the balloon increases, that means like the surface area increases, or the volume increases, or the radius increases, stuff like that. And so when you look at related rates, your goal is to find the missing value, whatever that is for the problem, and that will usually involve something changing, right? A rate of change, so our derivative. So when we have something like how quickly is the radius changing, right, that tells us we're looking for a derivative. And so here's the way this is pretty much always going to work. You're going to read the problem, write down the values you know, you're going to draw a picture. Pictures help immensely. Please draw a picture every single time. It will help you leaps and bounds. Draw a picture. You're going to find a formula that you can use to relate different things. Like, for example, in the balloon example, if we were to have the volume, right, and we wanted to find the radius, then we could always use the volume of a sphere to find that. So 4/3 pi r cubed, right, that has r in it, the radius, and that has v in it, the volume, and so that is a function that has both of those things in it. Then what we're going to do is we're going to take a derivative with implicit differentiation. Now here's the kicker. We're going to take a derivative with respect to t, which is time. So not r, not v, not any of the variables you have, time. So that means v, when we take that derivative, becomes dv dt, derivative of v with respect to t, time. So dv dt. And then on the other side, right? We had 4/3 pi, which is a constant that just comes out, and then r cubed. So we'd have 3r squared dr dt. So again, implicit differentiation. Remember, if I take the derivative of something that isn't what I'm taking, like the derivative with respect to, in this case t, I have to put that either, y prime or dy dx next to it. But this time our variables are all different. So instead of x, we're taking the derivative with respect to t. And so in our balloon example, we'd have v turning into dv dt when we take the derivative. We'd have 4/3 pi r cubed turning into 4/3 pi times 3r squared dr dt. Okay, then you're just going to plug in all the values you know, and you're going to solve it, and that's it. So that's literally all the calculus, is just taking an implicit derivative. That's the entire calculus. So once you draw your picture and you know what your values are, the hardest part is finding that function that relates them. So think back to geometry, think back to trig, think back to all that kind of stuff. Look for those. Look at the examples in the book and in the notes. And you can always talk to me if you need help figuring out what those equations look like. That's usually the hardest part of this, because once you draw the picture, it's easy to figure out where the values go. Once you have the equation, it's easy to take an implicit derivative, plug in what you know, and just solve like algebra. So focus a lot on that aspect of it. So that is related rates. 310 is linear approximation and differentials. So essentially, differentials are just kind of a rewording of linear approximations with the formula. So I'm going to leave that to y'all to read. I'm going to more explain what linear approximations are. If I have a function that's all wonky, so I'm just going to say we have a curve. So we have a curve, and let's say it's really hard to plug in values for this curve. Well, what I can do is, if I want to find this value, but it's really hard to figure out, but this one's easy, I can put a tangent line there, and I can use that tangent line to approximate where that curve is. That is literally it. So take a derivative, find a tangent line, and then rather than plugging in our number into the actual function, which may be difficult, we can just plug that into the tangent line. And so this pops up a lot when you deal with stuff like square roots. So for example, if I ask you what the square root of 4 is, you would say 2, hopefully. And you would say that because it's very easy to calculate. Now, if I ask you what the square root of 4.01 is, you would give me a blank stare and or reach for your calculator. Okay, well, we can actually approximate what that is with one of these linear approximations, right? So we would take the square root of x, right, and we'd stick a tangent line at 4, because that's easy to figure out, and then we just go eep up to 4.01, plug it into the tangent line instead of the function, and that would give us a close approximation of what that value would be without having to do terrible calculations or resort to our calculators. So that is what 310 is going to be. 311, we're skipping that's hyperbolic functions. There's things called hyperbolic trig functions that are pretty neat in a couple applications, but right now we're going to leave that by the wayside because most of what that section is just a couple derivative formulas. It's not actually any of the fun stuff, so you'll encounter the fun stuff later if you decide to continue your mathematical career. But for now, we'll move on to min-max values. So essentially, minimum and maximum values, there's two types. There's absolute and relative. So relative mins and maxes kind of look like hills or valleys. So if you imagine a function going like this, right, you have a hill, so the top of a hill is a relative max, and the bottom of a valley, right, is a relative minimum. So this may not be the smallest value the function takes on, this may not be the biggest value a function takes on, but regards to what's around them, right, they are the biggest and smallest. So relative, meaning like what is around them, those are min and max values. Now, one important thing with min and max values, when we talk about where those values are, we talk about an x value. So I can say I have a relative maximum at x equals 3. So we use the x-axis to tell us where things are. Now the actual minimum and maximum values, we use y's, because those are the values the function is taking on. So I can say I have a relative maximum at x equals 3 of y equals 12. And that would mean at x equals 3, the function takes on a value of y equals 12, and that is my relative max. Okay, so those are relative maxes and mins. Finding those is actually fairly straightforward. All you have to do is take the derivative and set it equal to 0. That's it. Because if you have the top of a hill, right, and it works the same for the bottom of a valley, right, you have a tangent line that goes across, and at the top of the hill, the tangent line is lying flat across it. Well, what's the slope of a flat line? 0. So if we take the derivative, which gives us the slope of our tangent lines, we set it equal to 0, it'll give us the x values where the function has a tangent line of slope 0, which is exactly the relative mins and maxes. So you'll learn a little bit more about that and why exactly those are the only spots that can happen, but that's pretty much that. The other thing is absolute mins and maxes, which are literally just the biggest value a function takes on, the smallest value a function takes on. So you'll learn some of that as well. The way we'll find those is fairly similar. Basically, we'll look at the relative mins and maxes and see if any of those work, and then we'll see what happens at kind of the end of our intervals. So if you imagine taking a function trapped between like 1 and 3, right, we would be able to look at that function in between and see where the relative mins and maxes are and test those, and we'll also test what happens at the end. Now, one thing can happen here that's very weird. Let's say we have just a regular y equals x line, right? So the most basic line. So this line, right, is going to go all the way up to positive infinity and all the way down to negative infinity. So what's the absolute max and the absolute min of that line? Well, there isn't one really, because if you pick an absolute max, right, it keeps going. So let's say we decided that this value, this y value, was the absolute max, but the line keeps going, so there's something bigger than that. And then it keeps going, so there's something bigger than that. And this basically goes on forever. So what we would say in that case is the absolute min and max do not exist, D and E, or the function does not have an absolute max or an absolute min. So that's something to watch out for with those. And the cases where you'll need to watch out for that, you'll be able to read about and see. The last thing is the mean value theorem. And so essentially what that says is there's going to be two theorems that pop up in here. There's Rolle's theorem, which is kind of a like smaller version of the mean value theorem, and then there's the mean value theorem. And so the mean value theorem basically says if you have a function on an interval, it's continuous and differentiable. So it starts here and it ends here, and it does some wibbly wobbly stuff in the middle. Right? At some point in between here and here, there's going to be a point where the tangent line to the curve is parallel to the line between these 2 points. You know, it's probably pretty hard to imagine with me just saying it. So take a look at the book, read over the theorems, and look at the pictures in there. That will help a lot. One thing I want to make clear with theorems is that you need to be aware of what the conditions or hypotheses of that theorem are. So for example, the mean value theorem says that you need your function to be continuous on that interval and differentiable on that interval. Meaning, when you go to use the mean value theorem, you need to check those things. You don't just get to use the conclusion of the mean value theorem for free. You have to make sure that that is actually the case. So that's something to be aware of just in general whenever you're looking at theorems in mathematics, is you want to be very aware of what the conditions and the hypotheses are. So this video has already gone 10 minutes longer than I thought it would, but that's fine. Hopefully this helped out a bit. Hopefully the tests are going well. If you have any questions, please feel free to email me. YouTube is also a good resource, especially for the very visual stuff. So like related rates is a good thing to search on there. The mean value theorem is a good thing to search on there. Anything that's very visual that you kind of need to see, I would look at YouTube for that. So Other than that, like I said, any questions, feel free to email me or contact me. And otherwise, have a great week.